Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 50, and this problem gives us a statement saying that this carbanion, this alkyne, is more stable than this alkene carbanion. So why is it that this alkyne carbocation is less stable than this alkene carbocation? Well, let's look at the orbitals for each of the following statements. So they were giving us the statement saying this is true, then why is this true? So if you look here, we see that we have determined the orbital of this carbon here. So this carbon has a lone pair of electrons, giving it a formal negative charge, and it has another substituent group here, which is going to be your alkyne. So this carbon has two unique things attached to it. So we have one of it being the lone pair, one of it being the substituent. So it has sp. This carbon is sp hybridized. So we know that s to the power 1, p to the power 1, so 1 plus 1 equals two unique things attached to the central carbon. While here on this carbon, this carbanion, we have one group here, one group being this hydrogen bonded to this carbon, one of them being the lone pair electrons, which gives it the formal negative charge. So we know that there's three things attached to the central carbon, so it's going to be sp2, because s is to the power 1, p is to the power 2, so 2 plus 1 equals three different things attached to it. So we know that negative charged or lone pair electrons are more stabilized when they're in a lower or smaller orbital. So we know that s orbital is smaller than the p orbital. So when your lone pair is in an orbital with a higher percentage of s characteristic, that's going to be more stable carbanion. So we know that this is 50% s characteristics, while this is 33% s characteristics. So because this alkyne has larger percentage of s characteristic, we know that this carbanion will exist in a smaller orbital, being closer to the nucleus and being more stabilized than this alkene carbanion that's going to be further away from the nucleus and less stabilized. So now, why is it that when we have a carbocation, why is it that the opposite is true for stability? Why is it the alkene more stable than alkyne? Well, now you got to remember, well, what's your nucleus? Your nucleus is positively charged. These electrons are negatively charged. So it makes sense. If the positive and negative charge were closer together, that'd be more favorable. So S is smaller, it's closer to the nucleus. So that's more favorable. But now we have a positive charge. The nucleus is going to be positive charge. So a positive and positive, they repel each other. So obviously you would want your positively charged carbon atom to be as far away as the nucleus as possible. So you would want something that has a greater percentage of p characteristic to make sure that this positive charge exists in an orbital that's further away from the nucleus. So it's going to be less repulsive and less and more stable, you could say, actually. So less repulsive and more stable. So if this is your positively charged nucleus, if this is your s orbital, then you have your p out here. So obviously you have your p is further away from your s. So you have s here and then p here. So obviously if you want your negative charges to be as close to this positive nucleus, but you want your positive charges to be as far away from your positively charged nucleus. So if you use the same sp2 or sp, you see that now if we look at the p orbital, this has 66% p orbital, while this still has the 50% p orbital. So obviously something that has 66% p orbital would be more stable for a carbocation with its positive charge than something with only 50% p orbital.